Right, so I'm going to be talking about this Mobius transformation f of z, which I claim maps the upper half plane to the unit disk. Now you can break it down to you can rewrite it as 1 minus 2i over 2 plus I, and so that tells you what the elementary, what it's a composition of elementary Mobius transformations, and we can track precisely how each of the regions get mapped at each step. So first of all, we start out with the upper half plane, right? I've partly drawn it here. So z gets mapped to z plus I, so then that means that the region gets moved up here. Okay? So it gets shifted up by 1, right? Gets translated by I, so it goes up by 1. Next, we're going to take z plus I to 1 over z plus I. Now that's actually going to map it to this region right here. Okay? So we're going to go from here, and then the inversion is going to take us to this circle right here. Now, you've got to be careful because a geometric inversion is different from this kind of inversion. Okay? So geometric inversion takes 1 over e to the I theta to 1, let me say that again. So a geometric inversion takes the complex number r e to the I theta to 1 over r e to the I theta. Right, this is the geometric inversion. The complex inversion 1 over z takes theta to minus theta as well. Okay, so let's first understand what the geometric inversion should do. So if this is let's first figure out just where this line gets mapped to. Well, this is the circle that I'm inverting in. Right? This is what 1 over z does. It inverts in the unit circle. Okay? So I want to perform an inversion in the unit circle. Now, let's take this point and let's take some other point, let's say out here. Okay? Now, let me call this point O, A, and B. Now suppose that A gets mapped to A tilde under the inversion, but it's just going to be the same here. And B will get mapped to, let's say, somewhere around here. B tilde here, okay? Now, we've already discussed the property, this important property that the geometric inversion does, namely that the triangle AOB will be similar to the triangle B tilde OA tilde. And so that means that the angle that's given by BAO, so BAO, the angle BAO, which is 90 degrees, is equal to A tilde B tilde O tilde, which is just O. Okay, O gets mapped to O. Well, actually, sorry. Yeah, you don't take whatever point O gets mapped to. So A tilde B tilde O. Okay? Now A tilde is here, B tilde is here, and O is here, so that means that this guy right here is also a right angle. This holds for any arbitrary point B on here, so that means that actually this point right here, this B tilde, as I move B tilde around, this traces out a circle because this right here is a right angle. This is the diameter of the circle, which means that the circle that we get is centered at this point, and it has a radius of a half. So, this is the circle we get if we do a geometric inversion. Let me draw it in red. Okay, I mean, it's not the most convincing circle I've drawn, but this is what we should get. Now, this is a geometric inversion. To get 1 over z, we need to take theta to minus theta. Okay, and so that goes over here. Now, we should also convince ourselves that this happens algebraically as well. Okay, so let's convince ourselves that actually the region is indeed mapped to what it should be. Okay, so let's suppose that we've got well, what we're going to do is we're going to show that the complex inversion z to 1 over z maps circles to circle lines to circle lines. We're going to start out with assuming that we have a circle, but of course, you can go backwards. Okay. Of course, it's obvious that a line through the origin will get mapped to a line through the origin, so we don't bother tackling that case. Okay, so let's say that we've got z. So let's say we've got a point. Let's say we've got a point on a circle. Okay. Then w in C is on the inversion of the circle if and only if 1 over w minus squared is equal to this. Okay. Now rearranging, we get r squared is equal to 1 minus aw minus a bar w bar this divided by w squared, which you can rearrange to give you this. Now this tells you something very important. Okay, so if the radius is equal to the center, right, meaning that if the circle passes through the center, if the circle passes through the origin, then this is going to be 0 and you're going to get a line. Otherwise, you're going to get a circle. Okay, so this is saying that all circles that pass through the origin gets mapped to a line, which we already know, right? In this case, this is indeed what we have. So let's check that. So we said that the circle, we claimed that this region right here, where this is the point I, gets mapped to this circle right here, centered at minus I over 2 with radius 1. So let's plug in a is equal to minus I over 2 and r is equal to a half. And let's see what happens. Let's check that this works. Left hand side is 0, right hand side becomes 1 minus 1 plus I over 2 w minus I over 2 w bar equals 0. Okay. And so if I come over here for a second, so w minus w bar divided by 2I is equal to 1. Right? Yes, that's correct. Okay, and that means that the imaginary part of w is equal to 1, which is precisely the line y is equal to 1. So this works. Yippee. Okay, so where we left off, we had taken z to 1 over z plus I. Right, and that gave us this nice little circle right here. Now I'm going to multiply it with minus 2I. So, okay, I've drawn it wrong here. There we go, yeah. So, minus, so this was 1 over z plus I. Okay, now I take it to minus 2I over z plus I. So what does that do? So that rotates it. So the I rotates it clockwise by 90 degrees. And then you're scaling by 2. Sorry, the minus I is rotating it. And then you scale by 2. And you get this large circle right here. Finally, you add 1. And that shifts it. And we end up being precisely... we end up precisely in the unit disk. Okay, and so, of course, we've only technically checked the boundary, but the interior gets mapped to what we want, right? That's actually super duper easy to see, because if you take any point, let's say here, right, when you do the inversion, it's clearly going to get mapped to a circle inside here, right? Because the inversion swaps the inside and the outside. Okay, and then when you do the transformation here, rotation with scaling, you end up here, and then when you add 1, you finally end up in the interior. Okay, so that's that. Now, what if I wanted to map What if I wanted to map instead the lower half plane to the unit disk? Well, that couldn't be easier because this maps the upper half plane to the unit disk, so just take the inversion again at the very end, right? So, if we were keeping track of the lower half plane, we would have ended up on the outside instead, right? And in this case, if I want to end up on the inside, just take this resulting thing and do 1 over that. So this maps the lower half plane to the upper half plane.